Hi and welcome back to Gaffey's Grinds. In this video, we are going to do another exam question walkthrough. We're looking at question 5s in this playlist, and we are going to look at the 2018 question 5. Now, typically, question 5 usually comes from areas like history of atomic structure, maybe radioactivity, mass numbers, isotopes, relative atomic mass, mass spectrometers, or chemical bonding. So those are the general areas that this question 5 normally comes from. Now, this question happens to be mostly about different isotopes of atoms, different masses, relative atomic mass, mass number, the mass spectrometer, and then finally the radioactivity. So if you feel like you want to spend maybe 5-10 minutes revising those sections in your revision book, and I always tell my students that this here is a great revision book. It's called Essentials Unfolded, Leaving Cert Chemistry. And some of you may have your own notes already as well, but if you want to do a quick skim through revision, or maybe some flashcards, whatever you have of these topics before we begin, that might be a good idea to do that now, pausing the video and doing that now. Okay, so now that we have gone through that, and if you've had a quick revise, always maybe a good idea if you haven't seen a topic for a while. But if not, then hopefully we're ready to jump in. So let's jump straight in. And as we see, the first line, part A here, question 5, part A, asks for 2 definitions. The first definition is referring for the mass number. And the second definition is asking about the definition for relative atomic mass. Relative atomic mass. Okay, now some of you may remember them definitions and be ready to go ahead, pause the video and write about them now, pause the video, do that now. All right, for those of us who aren't sure and are struggling, well, let me tell you what I can give you an example of here. Say we have a tile or an element from the periodic table and say it's oxygen. We learned that oxygen has an atomic number of 8 and it has a mass number of 16, okay? So what do those numbers tell us? This is the mass number. We also know that on a more modern, or maybe I would say a leaving cert periodic table, oxygen would look like this. It's O and it's 8 is the number, and then I think it's like 15.99. Okay, so this here shows the relative atomic mass instead of the mass number. So why is this number a decimal? That's what the difference between mass number and relative atomic mass. So now that we've gone through them, 15.99 versus 16, what's the difference between these two numbers? Pausing the video and writing that down now. All right, checking out the marking scheme here, as you can see, define part 1, the atomic number is the sum or the combined number of protons and neutrons in the nucleus of an atom, okay, or the number of protons and neutrons in the nucleus of an atom. That's what the mass number tells us. It's worth 3 marks. Give yourself 3 marks if you got that right. Right, what's the difference between the mass number and the relative atomic mass? Okay, well, the relative atomic mass, first of all, is an average. That's why it's not a round number. It's a decimal number. It's an average of the mass numbers, or the average mass of the isotopes of, because remember, some atoms have different isotopes. So for example, carbon has the carbon-12 isotope, but there's also a carbon-13 isotope, and there's also a carbon-14 isotope. And all of these exist and contribute to the mass of carbon, because in the world there will be a certain amount of each of these, and we have to account for all of these. So see what it says, it's the average mass numbers, or the average masses of the different isotopes of an element. So carbon has 3 elements, so to take the average masses of those, but also take their abundances into account. So carbon is mostly 99% of the carbon in the world is this isotope here, carbon-12. So it's more heavily weighted when we're working out the mass number. And that's why the relative atomic mass is closer to 12, it's 12 point something, rather than closer to 13 or 14, because most of the carbon in the world is carbon-12. So let's go through that again. What do we want to have here? We want the average masses of an atom, or average masses of isotopes of an element, taking abundances into account, and then we want to compare that to 1/12 the carbon-12 isotope, okay, or based on 1/12 of the carbon-12 isotope. Now, I can't go into teaching that whole idea again, where that comes from. I've done this on videos before, so if you need to revise that, I suggest you go back if that definition makes no sense to you, but it should do if you've done it with me before. Then this is just a revision of it. Okay, so it's the average masses, the isotopes of an element, taking their abundances into account, and it's compared to or based on 1/12 the mass of a carbon-12 atom. All right, let's go on to the next bit. It says a sample of magnesium metal is introduced into a mass spectrometer and vaporized. What were the next three fundamental processes that occurred in the mass spectrometer? This is part B. We have learned before, what are the stages of a mass spectrometer? You're told that we vaporize the sample first, vaporized. So that was the first step. What happens then in the mass spectrometer? The next three steps. So pause in the video and writing those down. Now fill in the bullet points here. What's the next three stages? Stage 2, stage 3, and stage 4 processes that happen in a mass spectrometer. Do that now. Okay, so again, that's something you just got to learn. First of all, we have to ionize the sample. The atoms will not move in an electric field unless we ionize them. So we have to turn them into ions. We do this by firing electrons at them, and this makes them have a charge. They then get accelerated down the tube of the mass spectrometer. So they basically get fired down the tube. So it's ionization is step 2. Acceleration is step 3. And then we want to separate them. That's what we're trying to do in the mass spectrometer. Separate them based on their masses. So we apply an electric field, and this pulls the lighter ones around the bend, and the heavier ones keep going straight, essentially. So this here is separation or deflection in a magnetic field. So separation is step 4, sorry. So that's what you should have had: ionization, acceleration, separation. It actually says here the order of responses is not important. So they would have given you the 3 marks, even if you mixed up the order, which is quite nice. What else does it say? Award no marks for vaporization or detection, but do not cancel if both are listed. Okay, so they've already given you vaporization. Detection is the last one, and they didn't ask for that. They asked for the next 3. Okay, all right. Cool, so that is part B done. Moving on to part C, what does it say? It says the mass spectrum of a sample given below shows that magnesium has 3 naturally occurring isotopes. Okay, so looking at this graph here, what I want you to do is pause the video and have a scan of this graph. But what is it telling us? It's telling us the mass number of the isotope. So I see 3 isotopes. There's an isotope with a mass number 24. There's an isotope with a mass number 25 and a mass number with an isotope 26. So this is a typical readout from a mass spectrometer. And as you can see here, the percentage abundance of each isotope is listed here. So it's mostly 79% of the magnesium in the sample is magnesium 24. 10% is magnesium 25 and 11% is magnesium 26. Okay, so what you have to do is you have to use the data given to calculate the relative atomic mass, and it says correct to do 2 decimal places. So I'm highlighting that now. You should do the same because that's important information. All right, so what I would like you to do for part C here is to pause the video if you're able to and write out calculate the relative atomic mass using the abundances, the percentage abundance, and the masses. Pause the video, do that now. All right, so if you weren't able to do that, I'm going to show you how to do this. To find the relative atomic mass, you need a formula, okay? What you need is the percentage abundance times the mass of isotope 1. And this is going to be an average, so we're going to add up the different isotopes. Then we're going to do the percentage times the mass of isotope 2. And we're adding that together. And then we're going to add, that's isotope 2, and then we're going to do the percentage times the mass of isotope, percentage by the mass of isotope 3. And all of that divided by 100 will give us the relative atomic mass. Now remember, at the end, we should get a number that's between 24 and 26 somewhere. It has to be in here because we can't have an average of these 3 masses that's outside of them 3 masses. So the number has to be in there. That's how you'll know if you got it right or not. So I'm going to, now that you have the formula, you should be able to do that. So pausing the video and figuring out the relative atomic mass now. All right, so over here, you should only be playing if you've got this done. Here is the final answer, 24.32. So as you can see, there's the first isotope, there's the second isotope, there's the third isotope. Add them all up, you get a number. And then obviously that number is way too big to be a mass. We have to divide that by 100 to get mass, 24.32. Okay. Notice in here it says 24.31 is without any work shown. If you don't show any work, you just did it on the calculator and you got 24.31, you get no marks. So this is the importance of showing your work. 24.31 where work is shown should be marked consequentially. Okay, so you'll get most of the marks for that if you've shown the work. Okay, so really important to show the work. All right, back to this. Now we're moving on to the radioactivity portion of the question. So that's the mass spectrometer and isotopes over to an extent. We're now moving on to radioactivity part D. All right, so it says here the radioisotope carbon-14 emits beta particles. So there's important information, beta decay, and has a half-life of 5,730 years. That's going to be important. So beta particles, it's carbon-14, has a half-life 5,730 years. All right, so the first thing we'll jump into a definition here. It says that you guys have to define radioactivity. Okay, so part one, what is radioactivity? So describing that as best you can now. Pause the video and do that now, please. All right, if you're struggling here, think about what happens in radioactivity. In radioactivity, we have a nucleus that is unstable. So there is an uneven or an unusual amount of neutrons compared to protons. So some elements have a strange amount of neutrons. They have an isotope that has extra neutrons, and that makes them slightly unstable. Okay, so what's going to happen to those unstable nuclei? What's going to happen to them? And when that happens, what specifically usually happens? So that should give you some hints and help you write out the definition if you don't know how to do it. All right, over to the Martin scheme. As you can see here, it's the spontaneous decay, and they are requiring you to have this word spontaneous. Okay, so if you didn't have that in your answer, you're going to lose some of the marks there. It's in bold, that means it has to be there. It's the spontaneous decay. And what does spontaneous mean? Spontaneous means random and without trigger, no trigger. So there's nothing that sets this off, it just happens randomly. So some atoms just break down all of a sudden. It's very hard to predict when any particular atom is going to break down, but it does happen periodically, okay, just randomly. So spontaneous decay of, instead of decay, you could say disintegration, breaking up, or splitting of a nucleus. Okay, so spontaneous breakdown of a nucleus with emission of different types of radiation, or you might have said of one or more types of radiation. Or another possible answer here, if you didn't say anything from this line, you could have also said something from this line with the emission of alpha, beta, or gamma rays. So anything like that. You had to have something from the first line. You had to have one section from here, and then you had to have one of the following. This one or this one here. Okay. So checking that to see, how would you, what do you call it? Mark your answer. If you were being super, and you should be super strict with yourself, if it was somebody else's work and you were deciding what they should get, be strict with them. What would you give their answer? So 2 times 3 here is what, 6 marks altogether, marking that now. Okay, like I said on the carousel on our quizzes, the definition there is right. It has this stuff in it. It has spontaneous decay of radioactive nucleus with the emission of one or more types of radiation. So if you're struggling with definitions, I advise you always to practice with the carousel, with the flashcards. Next one, what change takes place in the structure of a nucleus when an atom undergoes beta decay? Okay, so very interesting question, pretty common question. Change to the nucleus. Change to nucleus during beta decay, nucleus in beta decay. So thinking about what is beta decay and how would you describe the process that happens to the nucleus? Pausing the video and writing an answer to that now. All right, so beta decay involves the splitting of one of the subatomic particles into 2 other subatomic particles. So that should give you a hint. What splits into what? Okay, and then what happens to the remainder, what we have at the end? What happens to the thing, the particle that's the resulting particle at the end? Does it stay in the nucleus? Does it get kicked out? What happens to the nucleus? All right, so hopefully we have an answer for that now. Okay, a neutron changes into a proton. That's what happens. Neutron splits to a proton. 6 marks, nice, but you have to know it, right? And an electron that is emitted from the nucleus. Okay, so we have a neutron, and a neutron is actually made of a proton combined with an electron. That's what makes a neutron. Okay, so a neutron is actually made of a proton and an electron forced together. That's why it's neutrally charged, because you have a plus and a minus. But when a neutron decays, the electron is fired out of the atom. Okay, so the electron gets fired out, which leaves behind the proton, and the neutron is gone because it has split into a proton and an electron. So the nucleus will now have an extra proton, and that electron will have been fired out of the atom as a beta particle. Okay, you could also give it as an equation. I don't really teach my students to do it like this, but some of you may have come across this. This is fine too. One neutron with a mass of 1 and a charge of 0 splits into one proton with an atomic number 1 and a mass number 1. Okay, so that's it. On to the next bit. Write a balanced equation for the beta decay of a carbon-14 nucleus. Okay, so we are going to pause the video here, and some of you will be able to do this by yourselves already. Pausing the video and doing that now. Okay, and if you're not able to do this, well, then I'm going to try and help you. Okay, so we're starting with carbon, and it's the carbon-14 isotope, so it has a mass of 14. Go into your periodic table. What is the atomic number of carbon? Find that now, please. Pause the video. Okay, so hopefully you can see that this is carbon with an atomic number of 6. Now we're going to use an arrow to show that this splits. And what we want to know here is we want to know what does it split into. So you're obviously going to have a symbol. Is it still carbon or is it a new element? You're going to have a mass number. Is it still the same as, is it still 14 or has it changed? And you're going to have an atomic number. Is it still 6 or has it changed? Plus, of course, we have a beta particle, which we can show like this, or sometimes you can just show it as an electron. Now, of course, the electron has a mass number of 0, and we know it has a charge of -1, but it doesn't have an atomic number. All right, so pause in the video and see, can you work this out here now, please? Okay, so if you can't work it out, remember what we said in the above. What happens in beta decay? A neutron splits into a proton, which stays in the nucleus, and then the electron is fired out. So think about the changes in the nucleus and what that's going to do to the numbers here. Okay, so as you can see, a neutron splits into a proton. So one of the neutrons splits into a proton, which puts an extra proton in the nucleus. And that should mean that you have the number 7 down here now. Okay, so I'm actually going to make that a little bit bigger. I'm going to zoom in here and make this box just a little bit bigger. So we have an atomic number of 7 now. Okay, 7. So that means that this element cannot be carbon anymore. Okay, the next thing we want to know is, how does the mass change? Yes or no? Okay, so we're going to do a before and after decay here. Before and after. All right, what I want you to do is count up the number of protons and neutrons before, and now count up the number of protons and neutrons after. Pause the video and do that now. Okay, so as you can see, in the beginning, we have 6 protons plus we have 14 minus 6, 8 neutrons. 8 neutrons, and that's a mass of 14. That makes sense because that's what it is here. Look. Now, after, we know we have an extra proton. So we have 7 protons, and we know we have 1 less neutron because the neutron split into the proton, so plus 7 neutrons. But the mass is still 14. So that tells me that this number up here is still 14. The last thing to check is, what is this element? So go to your periodic table if you haven't done this already and find the element that this is. This element is, what element is this? This carbon, and this is now nitrogen. So this is now the nitrogen-14 isotope. Okay. All right, well done if you got that right. If you didn't get this right, I highly suggest at this stage you go through your exam papers, find another question that has a beta decay equation, ask you to do it, and practice doing that now. Because now is the time to really practice revising by doing another one for yourself. Do that now. Okay, so now that hopefully we have radioactivity done, and again, if you're on study clicks, you can always go to the radioactivity section and find another one where it asks you to do a beta decay equation. But I do highly suggest that you do one the same as I've done now, and that's your revision of this. Okay, on to the next bit now. All right, so what I'm going to do is I'm going to ask you to pause the video, and I'm going to ask you to read this little section here. Do that now. Okay, I'm going to also ask you to go back up and read this sentence again. Okay. All right, now we're going to read this. Right, so let's figure out what's going on here. Okay, there's two parts of this question. First of all, here it says explain, so there's the question that we'll have to answer. But then down here it says what mass. So these are two separate questions that are shoved together in one section, and we might easily miss the fact that there are actually two parts to this. So this is VI. No, it's not. It's IV. Sorry, part 4, IV. And we're going to do the first bullet point here. It says explain why the fragment of U must have contained 3 by 10 to the 12 carbon-14 atoms 5,730 years before the analysis. Now, just for reference, in this section up here, it said that when we tested the sample, it contained this many carbon atoms. Okay, so what's the significance of this number here and this number compared with that number? So those two numbers, what's the significance here? Okay, so you're asked here to explain. So pause in the video and writing this down now. Try and write an answer for that. All right, well, if you haven't copped, you should notice that this number here is twice the amount of that number there. It's 2 times the amount. Or in other words, this number here this is today is half the number of atoms of what it was that many years ago. Okay, so this is half of this. Okay, that number there, 1.5, is half of 3. So that should again help you to explain why that is. Pausing the video now. Okay, right, we're going over to the mountain scheme. What does it say? Explain why. Well, 5,730 years is the half-life. And what is the half-life? The half-life is the time taken for half this nuclei in a radioactive sample to decay. So after one half-life, we will have half the number left. So if we have 1.5 by 10 to the, what was it? 1.5 by 10 to the 23 or whatever it was it? By 10 to the 12, then we should have had twice that number one half-life ago, 3 by 10 to the 12. So explain why. Well, 5,730 years is the half-life. So it makes sense that one half-life ago, we would have had twice the amount of atoms that we have now. I'm also going to get you to pause the video and have a look at the other answers there and see if you can get any of them to match your answer. Pause the video. All right, that was worth 3 marks. Okay, now on to the next one. All right, what mass of carbon did the fragment contain 5,730 years before the analysis? Okay, what mass of the carbon? So this is the second bullet point here, and you're trying to find the mass of carbon. And that's 5,730 years ago. Pause in the video and working that out now. Okay, the answer that you should have got here is 7 times 10 to the minus 11 grams. If you got that right, well done. If not, stay tuned here for hints on how to do it. If you did get that right and you finished the question, go ahead, add up your marks and see what you got out of 50, and that will give you an idea of where you're at on this question. All right, so let's have a look at some hints and tips here for you. First of all, how many atoms did we have 5,730 years before the analysis? Well, it told us in the first part that 5,730 years before the analysis, you had this many carbon atoms. Okay, So you have a number of atoms of carbon. Okay, and what you need to do is find out how many grams that would be. Now, of course, you can't do that without going from atoms to moles of carbon and then going to grams of carbon. Okay, so now that I've shown you how you would do that, you should be able to work your way through and get this answer in grams. Pause the video and do that now. All right, so if you weren't able to do it, the first thing we're going to do is we're going to write down how many atoms we had. 3 times 10 to the minus, oh no, 3 times 10 to the 12, and that's atoms of C. So I'm writing down what I have. And I want to go to moles of C. So I'm going to times by a conversion factor, which gets rid of atoms of C. So I'll put that on the bottom here. And then what am I going to put on the top? Well, I want to go to moles. So I'm trying to do this conversion. So moles of C on the top. So you pause the video and take over if you were stuck and now you understand. You pause the video and take over from here now. Okay, so hopefully you understand that for every 1 mole of carbon, you have Avogadro's number of atoms, 6 by 10 to the 23. Okay, good. Now you can either do equals here, okay, and get a number of moles and then do grams, or you can just keep it going. So I'm going to keep it going here without doing equals and then just say, okay, remember we want to get to grams. So this time we want to cancel moles of C. We're going to put moles of C on the bottom and we've got grams of C on the top. So moles have cancelled. And the next thing we want to know is how many grams are there in 1 mole. So if we make it 1 mole, how many grams are there? Okay, of course, carbon has a mass of, now it's carbon 14, so don't let that catch you, okay? That's where you might have got caught. If your number was wrong, I reckon that's it. It's carbon 14, so it's a mass of 14. You might have been tempted to go to your periodic table and use a mass of 12 from the periodic table, but this is only carbon 14 atoms, so that could be really, that's a really tricky little snippet there, okay? And I'm just looking at the marking scheme here, and you're losing quite a lot of, you're going to lose a lot of the marks if you used 12. Okay, so I think you lose 3 of the marks out of the 6. All right, so you really had to think and be careful. It was carbon 14. Look at that, and look at how they worded the question. So what mass of carbon 14? They were very specific to suggest it here. Okay. All right, so when we put this in the calculator, look at the units that we're left with. Grams of carbon, which is what we wanted at the end. And this is grams of carbon 14, of course, and that's why it has a mass of 14. Get your calculator out. I just want to double check that this does give us the right answer. I don't want to be telling you a sum that's wrong. 3 by 10 to the 12. And that's times by 1 over 1 over 6 times 10 to the 23. 6 times 10 to the 23. And all of that then is times by 14 over 1. And yet that gives me 7 by 10 to the minus 11 equals 7 by 10 to the minus 11. And that's, of course, grams of carbon 14. Now, well done if you got that by yourself. I reckon that this little tricky bit, might have caught some of us, this 14 grams. So they're really, again, really challenging you. And that was worth 6 marks. So go through your question now. Out of 50 marks, how do we do? Are we on for H1, H2, H3? Where are we at on that question? And again, the more of these questions that you can get into the H1, H2 zone, then that's going to help us if that's what we're targeting. Okay, but these little bits, these little bits here, these tricky bits, they're thrown in to try and separate the higher, the H1, H2 students from other students, because they have to have a way to see who's able to solve all these problems. Again, you can get better at these things by just practicing lots of them. That's all I can suggest. All right. I don't think you're going to find another one that's exactly the same as that in the exam paper. So there's no point in trying to learn off this calculation, because it might never come up again. You have to learn to think about the problems that are thrown in front of you. Take your time and work your way through and really read through what they're at and what they're giving you. If you really read this, then you wouldn't have missed that little thing. Okay, So that's it, guys. I shall see you in the next video. I hope you've done well on this question. I think it was quite a nice question if that had come up when I was doing the leaving cert. I think I would have been pretty happy with that. So again, these are types of questions that you need to be getting 40 out of 50 plus in if you want the H1s, H2s, 60 plus in if you want the H4s, H3s, H4s. Okay. All right, guys, that's it. I shall see you in the next video.